Thank you very much. So today we continue, and I will start by slowly recalling how my talk and the talk of Matej ended. So my talk ended with such a diagram. We had the usual C to the N. This is where representations of a matroid lived. And I told you that maybe we should think about it as diagonal matrices. Then we had this slightly funny compactification that, in a way, is maybe better than just compactifying to a projective space because it really remembers that there was a distinguished system of coordinates here. Then we had a Segre embedding, which simply meant in every P1 choose one coordinate and multiply your choices. And here we subdivided the choices according to how many times we chose the second coordinate. So these were really just inclusions. Now, when we were trying to contract C star orbits here, well, here we got the projective space. Here we got a new variety known as the permutahedron, which we could have thought as a blow-up of this thing, or simply the image in such a product of projective spaces given by all minors of all possible sizes of the projectivization of diagonal matrices. Okay, and above we had something that so far we called analogous in the world of tensor, where instead of starting with diagonal matrices, we just started, let's say, with, let's assume that dimension of V is dimension of W. So I can think about this just as n by n matrices. And again, we took a strange compactification. Yeah, so there is a big open, Zariski open piece in a Grassmannian, which are just n by n matrices. Yeah, so these are those that have, if you write it as a row span, the first minor non-zero, and then you can make it identity. Then the Grassmannian has a Plucker embedding. Here I wrote in a strange way the wedge n of V plus W. It breaks into such spaces, but you can think of it very much down to earth. Plucker embedding tells you that if you take an n by 2n matrix, you have to remember all n by n minors. And this decomposition just tells you how many rows you take from the first part and how many rows you take from the second part. Yeah, so you can group minors. Maybe you take 2 from the first part and n minus 2 from the second part, and this would correspond to I equal 2. Okay? And again, we had Chow quotients. Well, here we just projectivized, but here we had this variety that we obtained by taking all minors of all possible sizes. So here are I by I minors of matrices, and you map to the product of projective spaces. And the magic is that points, so a general point in complete collineations, well, it simply corresponds to a C star orbit in a Grassmannian, which is like an invertible matrix up to scaling. And special points, well, they correspond to unions of such orbits that I like to call zigzags. Maybe there are questions about this diagram, like someone would like to hear more about some entry in the diagram. Okay, so I want to say this is much more than just the analogy. It's actually inclusion, and let's start with an easy inclusion. Clearly, diagonal matrices are inside n by n matrices. But using this, you get much more. You can see this P1 to the n as a subset of the Grassmannian. So for example, a point 1a1, 1a2, 1a3 will be mapped to the row span where the first part is identity and the second is diagonal matrix a1, a2, a3, and so on. Yeah? This changes. So if you compose this inclusion in the Grassmannian with the Plucker, you exactly get the Segre embedding. So if you happen to know Plucker embedding and not know Segre embedding, you could have defined it via composition with the Grassmannian. This space is much smaller, but it's included here in this space. And this goes farther to the lower row. So you could imagine one diagram on top of the other, where the arrows are actual inclusions, usual nice inclusions. Yeah, I mean, projectivization of diagonal matrices inside projectivization of n by n matrices. The permutahedron lives inside complete collineations. And well, this product lives inside this one. So it's like, you know, here I told you that this is given by all I by I minors of a diagonal matrix. But I by I minors of a diagonal matrix are in particular I by I minors of a general matrix. Here you have many more coordinates, but they will be all zero, because if you will not take a principal minor, you will not see it downstairs. Because, I mean, you just don't put zeros here. So this projective space is like a linearly embedded subspace here where you put a lot of zeros. Matej also defined you that for any linear space inside this space of n by n matrices, you can close it in the Grassmannian, and then you get you obtain what we call the generalized Schubert variety. So notice that if you happen in your space of n by n matrices to take the diagonal matrices, it is a subspace of n by n matrices, then the generalized Schubert variety will be simply p1 to the n. So this lower part is an instance of a generalized Schubert variety, where your space of matrices happens to be the diagonal space of matrices. Oh, huh?
Jumping from one tensor to two tensors?
No, so it will be all about three tensors. Oh, that's a very good question. So you know, I told you, oh, I will not tell you what's a matroid. I will tell you what's a representation of a matroid. It's just a linear subspace of C to the n. But imagine this conference is the other way around, that you are at the combinatorics conference and you would like to also present this picture. You can tell people, oh, I will not tell you what's a tensor, but I will tell you the representation of a tensor. And the representation of a tensor would be, of a three tensor, would be a linear space of matrices. And I think this is a very efficient way of thinking about the tensor as a linear space of matrices. And you can say, oh, it's not the same as a linear space of matrices, but up to GL action on the first factor, you essentially get all information about the tensor. So we are talking about three tensors, and we choose one of the vector spaces, we contract with respect to that space, and we are essentially trying to say how our linear space of matrices is situated in the space of matrices. Just like people doing combinatorics, they try to say how a linear space is situated with respect to coordinates.
The constructions are so nice, are natural somehow, right? That you call, do you think this call is still happening if you go, because your first is under it you have CN, you have the diagonal matrices.
Yes.
You basically have vectors, right?
Yes.
You go to matrices, you have matrices.
Yes.
Then you go try to do the same construction for three tensors, and then try to get the same diagram, the same kind of diagram, doing the same construction. And you go higher in the head.
This I haven't tried, but you would need somehow a very natural and nice compactification of the space of three tensors. So for matrices, I know a very nice compactification, a Grassmannian. For vectors, I know a very nice compactification, P1 to the n. For three tensors, I would have to think what's the correct thing. I mean, we can discuss it later. Currently, the story is about three tensors or matroids. I mean, the lower story matroids, the upper story tensors in something tensor V, tensor W. Maybe one of them needs a dual. Okay. So it's and if you see, for example, if you are trying not with a computer but on a paper to find tensor rank or border rank, it's really good to think about the tensor as a linear space of matrices. So for example, there is this beautiful theorem that rank is simply how many rank 1 matrices you need so that their linear span contains your space. And somehow, well, decomposing a tensor, a three-dimensional thing in your mind might be hard, but if you think about rank 1 matrices and you just want to contain some linear span, that's easier. It's something I learned from Jarek years ago. And when he first told me this, I said that this theorem is too simple to be useful, and I learned that I was very wrong. I mean, it's simple, and that's why it's very useful. Okay, we continue. So as I was saying, the conclusions from this diagram is that this matroid picture, in particular P1 to the n, is a generalized Schubert variety for diagonal matrices. But you can do the same if you take a linear subspace in this Cn, and then the closure in P1 to the n will be the same as if you embedded it to the space of n by n matrices and closed it in the Grassmannian, which means that every matroidal Schubert variety is a generalized Schubert variety. And it turns out that also classical Schubert varieties, as Matej told you, they are also generalized Schubert varieties. So maybe just to tell you what's the connection. So Matej told you that Schubert cell looks something like this, right? You have to close such a linear space in a Grassmannian to get a Schubert variety. But you can always rearrange the rows so that the identity is on the left and this thing on the right. Right? And by definition, the closure of this is a Schubert variety. And the closure of any linear space, in particular such a linear space, is a generalized Schubert variety. So those generalized Schubert varieties, they interpolate among classical Schubert varieties and matroidal Schubert varieties. It just happens whether your linear space happens to be a coordinate subspace made of Young diagram, or whether your linear space happens to be a subspace of diagonal matrices. And now are funny things, because there is this chromatic polynomial that counts something, but now nothing prevents you from defining a chromatic polynomial for a tensor. Because if we go back, well, how could we define a chromatic polynomial for a matroid? We had a linear subspace here, and we were closing it, well, it doesn't matter, here or here, let's say, in downstairs. And then we were intersecting it with first and last hyperplane here to get the coefficients of the chromatic polynomial. Well, you can do the same for a tensor. You will have a linear space here, you intersect it with a first or last linear space here, and you will get some meaningful coefficients, invariants of a tensor. New integral invariants of a tensor that I personally find very interesting. But you may object. I mean, okay, so you made some analogy. Okay, before I will object, let me make it slightly more formal. So our complete collineations, they live in products of such projective spaces. And as always, when you have a variety in a product of a few projective spaces, every single projective space gives you a hyperplane. It's a different hyperplane. And such things we call divisors for a variety. They are codimension 1 subvarieties if we intersect them with the hyperplane in the ith projective space. And let me call such a divisor Li. So there will be L1, L2, L3, and so on. And whenever you give me a tensor, I can projectivize L. This would be like a wonderful model of a tensor. It would be the analog of a wonderful model of a matroid. So this would be the closure of the of the projectivization of invertible matrices in L in the variety of complete collineations. And this we can intersect with those divisors. The only thing that we have to keep in mind is that how many divisors we intersect needs to be the dimension of the variety you have. And you get interesting numbers that we called, that's I think with Austin Conner and also with Rodica Dino and Tim Seinave, we call it characteristic numbers of a tensor. And for matroids, I mean, these are called mixed matroidal Eulerian numbers. But let me just give you one very easy instance. When you happen to take all of the diagonal matrices, then you get the whole permutahedral variety. And you can ask what happens if you just intersect with one, Li, 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 the same one. And these are very important numbers in combinatorics, known as Eulerian numbers. They count the number of permutations with exactly I descents. And then, well, if you start varying the Li's but keep the permutahedral variety, you obtain Postnikov's mixed Eulerian numbers. And all these numbers, they have now analogs for tensors. Yeah, you can ask what happens when you replace the permutahedral variety by complete collineations. Yeah, so you would get what I would, for example, call quantum Eulerian numbers. This procedure of going from diagonal matrices, especially to symmetric matrices, is very analogous to what happens when you go in physics from classical physics to quantum physics. Now, the main advantage that I like is that on different areas of this diagram, very strong people worked and had ideas how to push forward the theory. And what this allows you is, okay, you can rely, maybe you have your own new ideas, but you can certainly pick an idea that, for example, people had in matroids and try to apply the same idea for tensors, or you can pick an idea someone had for complete collineations and see what it will tell you for matroids. It goes both ways. And one of the idea goes back 150 years. I will try to show you this idea. I think it's an amazing idea because Schubert lived in times where all these Chow rings, cohomology rings, they were not really formally defined. I mean, higher dimensional geometry was very sketchy. But he was such a genius that he was able to operate in Chow rings without really having Chow rings. And he realized, so this product formally should be in a Chow ring. And he realized that there are relations in the Chow ring. There are other divisors. Yeah. So I told you that one way to construct all of those varieties is via blowups. And blowups change rank I matrices into something of codimension 1. And such a divisor is called SI. And he somehow managed to get relations among LIs and SIs and replace such a product by sum of many, many more products involving SIs. So it looked like he made a step back from an easy intersection problem, but those intersections with SIs were tractable. I will try to, if I will have time, make some pictures to at least persuade you why this happened later. Okay, so now comes objections from the audience. For example, you could ask, why should I be interested, right? Or you could say, you introduce integer invariants of tensors that were not seen before. If those numbers were interesting, mathematicians would already find them outside of combinatorics, right? I mean, tensors were not discovered a week ago. And if there are really interesting integral positive invariants, I mean, people would have found them. And I only gave you similarities to matroid theory. I mean, saying that something is interesting by just giving one similarity seems not enough. And concluding from this, you can ask, do you really think this could be new interesting invariants? Yeah, and I feel that during a talk, I should answer at least this last question. So my answer is yes, I think so. Okay. So let me continue. Uh, um, so one of the objections is that I have only given you relations to matroid theory, and who knows what's a matroid. Let me give you one more example of a generalized Schubert variety. So apart from diagonal matrices in the space of symmetric matrices, in the space of n by n matrices, there is also a linear space of symmetric matrices. Yeah? So you can ask, what happens when you are closing symmetric matrices in the Grassmannian? And what you get is so-called Lagrangian Grassmannian. It's a subvariety of the Grassmannian. So it parameterizes special subspaces of V plus W. Not every subspace will be a point in the Lagrangian Grassmannian. And it goes like this. You have to identify your W with V dual. So this is because, you know, when you are talking about a symmetric matrix, if you want to do it invariantly, there is no chance you can say when a morphism from V to W is symmetric. You can only say when a morphism from V to V dual is symmetric, right? Because that's a tensor in V dual, tensor V dual, and okay. So you have to identify your, and now we have oh, sorry, it should be I should say that. So remember, our Grassmannian was a Grassmannian of n-dimensional subspaces of V plus V dual. So now this will be n-dimensional subspaces of V plus V dual. And I claim that on this space V plus V dual, there is a strange skew-symmetric product. Namely, if you pick a vector and a linear form, and another vector and another linear form, so 2 points here, you can evaluate one linear form and the other vector and subtract, the other linear form on the vector. This is skew-symmetric. And Lagrangian Grassmannian parameterizes those subspaces so that for any 2 points of those subspaces, the product is 0, so-called isotropic subspaces. Yeah, and this is not so hard. It's maybe a 1-minute exercise if you write it an identity and a symmetric matrix. If you take two rows, you will see that pairing here and subtracting pairing here, the fact that the matrix is symmetric exactly corresponds to the product is 0. Okay. That's clearly not enough to motivate you, okay? So there are interesting varieties arising at disclosures of linear spaces in the Grassmannian, but it turns out that somehow I showed you like the lower layer when there is diagonal matrices. I showed you the upper layer where there are n by n matrices, and there is a third layer in between for symmetric matrices. Yeah, so every part of the diagram I have given you, somehow there is a corresponding thing for symmetric matrices. It's not only Lagrangian Grassmannian sitting between P1 to the n and the Grassmannian. The symmetric matrices come with their own Chow quotient by the C-star action, and this is known as the variety of complete quadrics. And again, you can define it in a few ways, but I hope that this definition will be particularly similar to the definition I gave you of the permutahedron and of complete collinations. So complete quadrics is the variety you obtain as the image of the map that is given as follows. You start from any symmetric n by n matrix. Well, you keep the matrix. You take all 2 by 2 minors. So what I wrote here is quite strange, but 2 by 2 minors of a symmetric matrix, they can be arranged in a bigger symmetric matrix themselves, and so on. Then you take 3 by 3 minors, 4 by 4 minors. For people who know representation theory, this projective space is slightly too big. So there are linear relations among minors of a symmetric matrix. And this is very funny. So what I will say might shock some people. So Plucker relations, the ones you know that are quadratic relations vanishing on the Grassmannian, they are also linear relations among minors of a symmetric matrix. You just have to interpret them correctly. So, you know, before Plucker relation was a product of two things, but now you have to take what indices the things in this product as what indices rows and minors of a matrix. So you may think, oh, tensors are the most interesting. Oh, maybe those matroids, they were done in combinatorics and Juniha made their great work. But if you go to the history, this one is the one, I think, where mathematicians were first interested. This is the one that Schubert was studying. And you can ask why was he studying such a thing? So the thing is that a symmetric matrix is a quadric, right? That's the same thing in characteristic zero. So Jarek would distinguish, but in characteristic zero, essentially a degree 2 polynomial and the symmetric matrix is the same. Yeah, if you take a symmetric matrix, you just multiply it by x1 xn and x1 xn, and you get the polynomial. So it remembers the coefficients of the polynomial. So first, let me give you the missing piece of the diagram. We have symmetric matrices. I told you that the closure in the Grassmannian is the Lagrangian Grassmannian. The Lagrangian Grassmannian under the Plucker embedding still lives in a big projective space. You still can do the Chow quotient and you get complete quadrics, which you could have defined as the blow up of the space of symmetric matrices in rank 1, rank 2, and so on. Or you could have defined it as the closure of the image by taking I by I minors for every possible I. Probably should start at 1. I mean, it wouldn't hurt, but it would be a point if I start with 0, where you take all possible minors of size I by I of a symmetric matrix. Okay, so what did Schubert have to do with it, and why was he interested in something that is between tensors and matroids? That's a really long time ago. That's like, well, certainly 19th century. So geometry was central there, and people were trying to answer such a question. You are in a projective space, and you want to do some counting, namely, well, you know, this goes to ancient Greece, like how many points on a plane determine a quadric, right? But you can put other geometric conditions. Maybe instead of passing through a point, you want to count how many quadrics pass through one less point and are tangent to a line, okay? And mathematicians realize that these are very interesting problems. If you are trying to count, so quadrics, like degree 2 polynomials, that go through A1 general points, A2, that are tangent to, so tangent to a point means just passing through a point. That are tangent to A1 general points, A2 general line, so on, AN minus 1 general hyperplanes. And these are hard problems, not so easy. If you try to naively solve them and write algebraic equations that characterize being tangent to a line, being tangent to a hyperplane, and just use Bezout, you know, in 19th century people were clever, they knew such things, but you get wrong answers. You just get wrong answers. That you want to count solutions of degree something equation and degree something equation and degree something equation, and you may want to say that, oh, the number of such solutions should be just the product of degrees. But this is very famously in all of those intersection problems a wrong answer. And the reason is that your equations usually tend to vanish on a positive dimensional variety, like, for example, double planes, or that seem to be tangent to everything. And well, this obviously creates problems. But well, without knowing much, so if you're a fan of Keller geometry, you can really consider this as an integral. If you are not a fan of scalar geometry, this just means count the number of points. And Schubert realized that the answer to this problem is exactly the answer. You have to intersect divisors L1, A1 many times, L2, A2 many times, Ln minus 1, An minus 1 many times on complete quadrics. Okay? So the right space on which you can do the counting, although the quadrics are parameterized by a projective space, the projectivization of symmetric matrices, this is not the correct space where you should do the counting. The correct space is really after the blowups. Yeah, so these blowups will make your equations not vanish on the base locus. So you need to take as many conditions as you have the dimension of your space of symmetric matrices, which is like n plus 1 choose 2 minus 1 for projectivization. But whenever you take that many conditions, you will get an integer, and that answers your geometric problem. Okay, so what is funny is that I think until this point in 19th century, this was considered easy. The hard part was how to attack this number. Yeah? How do you actually turn this product in the Chow ring that did not exist at that point into a number? And that was the main contribution of Schubert, and so beautiful, and it makes yet another connection of this highest tensor level to very classical geometry. I want to give you some taste what Schubert might have been thinking. But as I said, even with this formal expression, computing the number is very challenging. Yeah? Okay. So we have two types of divisors. We have the divisors that come from hyperplanes, but we also have in complete quadrics the divisors that come from rank I matrices. So in complete quadrics, rank I symmetric matrices form a codimensional set. This might be very counterintuitive. Maybe before we go further, I will draw you one picture. My students laugh that this is my favorite picture and I always draw it, so I should not disappoint them. We have Lagrangian Grassmannian, which I always draw as an egg. So it parameterizes subspaces in V plus V dual that are isotropic with respect to this product. So in particular, there is V and there is V dual. If you take 0 as linear form, clearly the product I have given you is 0. But there are other C star invariant subspaces in the Lagrangian Grassmannian. Namely, if you take a subspace, let me call it maybe for a subspace M, no, M would be for a matrix, maybe N, in V, you can take n perp in V dual, and then there will be a point n plus n perp. Yeah? If you are pairing vectors and linear forms that vanish on them, you will get always 0, so you will be subtracting 0. So when you fix the dimension of this n to be I, you get a Grassmannian GIV, which is a subset of the Lagrangian Grassmannian, and these are C star fixed points. A typical C star orbit, so a typical symmetric matrix, it corresponds to a point identity and a symmetric matrix A, and with a C star action, the orbit will start at V and go to dual. Yeah, so remember, our C star action just multiplies this part. So if you go with T to 0, you will land at V. If you go with T to infinity, this is like making this 0, you will get to V dual. But you will have problems where A will be not of full rank. So we have those Grassmannians, GIV, for every I. They are C star fixed. And there will be also shorter orbits. Okay. Now, why do I have a slide where I tell something about complete quadrics and I am drawing Lagrangian Grassmannian? Because I told you that complete quadrics is a Chow quotient of Lagrangian Grassmannian. So I want to tell you that a good way of thinking about points in complete quadrics is via orbits here or unions of orbits. Remember, in Chow quotient. So this orbit, this shorter orbit, will have will have too small degree. It will not correspond to a point in the Chow quotient. But as this orbit, for example, this point will degenerate to this point, the orbit will break. Yeah? So points in complete quadrics are exactly such zigzags. You go to one Grassmannian, then you go to another, then you go to another. It's like fixing a partial flag on V and taking full rank quadrics on the quotients. Okay? And now I can tell you on this picture what are SIs. SIs are precisely those zigzags that break at the ith Grassmannian. Okay, I don't know how Schubert did it, but he did. He realized that there are those SIs on CQ, and he even realized that there are relations among SIs and LIs. Yeah, so you can change. These are like two bases of divisors. You can change from one to another. Now, I don't know if anyone recognizes such a relation. This is a relation between fundamental roots and simple positive roots in type A system. Why does a type A system suddenly jump in? So there is a full flag sitting inside this variety, namely these are zigzags that break at every place. And you can prove that if you intersect with any divisor with this full flag, this gives an injection of the Picard groups. And the Picard group of the full flag is the type A root system. And the LIs, they go to twice fundamental roots, SIs twice positive simple roots. Yeah. I really find it amazing. It's like almost 150 years ago, people knew such things. And not only they knew it, they could use it in practice to solve problems. Because now, so remember, our aim was to compute LIs.
They are coming from the blower.
So SIs is the exceptional divisor for the ith blow-up. But how do you get the relations? I mean, how Schubert got them, I'm not really sure. It's probably he was a genius and he just wrote them. How I would get them is I would realize that I don't understand CQ, but there is a containment of full flag variety inside CQ. Full flag sits there. And hence, whenever you have a divisor in CQ, you have a divisor in full flag. And LIs translate to fundamental roots, and SIs translate to positive simple roots. And then I know relations. It's like, fundamental roots means E1 plus E2 plus E3 plus EI. Simple roots is like, I forgot, EI minus EI plus 1 or the other way around. Yeah, so this tells you that if you want to get a difference of two consecutive things, you have to take twice sum until the ith, subtract the sum until the I plus first, and subtract the sum until I minus 1. So it's once you have this translation to roots, it's very simple. That's how I try to remember it. Okay, so this looks crazy because LIs, well, they were just hyperplanes, and suddenly Schubert puts in those exceptional divisors, and he will pick one LI and translate it. So you can also use it the other way around. I didn't write the other relations because they are more complicated, but it's a linear system. If you know how to go from one basis to another, you have to invert a matrix. So you can also replace one LI by some linear combination of SIs. And you're in a ring. So instead of computing one intersection of LIs, you can compute such intersections when you have one S and the other things are LIs. Why this should be better? This looks horrible, right? I mean, but it turns out that you can build another variety, SR, that so we are looking at zigzags that break at the ith Grassmannian. And it turns out that you can identify them. Sorry, there is a projectivization missing. So it should be a projectivization of the second universal bundle of the Grassmannian times projectivization of the symmetric square of the quotient dual on the Grassmannian. So somehow when you take zigzags that break at a given thing, you can identify this space with a space that over every Grassmannian, you have product of two projective spaces. That these are symmetric matrices on the subspace you are on. Other one is the projectivization of symmetric matrices on the quotient subspace. So instead of doing intersection theory on complete quadrics, we can do intersection theory on such double projective product over Grassmannian. And this reduces to intersection theory on a Grassmannian. And Schubert, of course, was the world master on doing this. So this is something that he could carry. So main advantage is that nowadays, after Schubert, people thought about it, how to do intersection theory on this. There's a whole theory. I here wrote Pragach, Lasko, but there is Procesi, De Concini, like Torap, like at least 10 people. I remember when I first put my paper on it, and Professor Pragach wrote to me that his whole habilitation was about it, and he's very happy that people are catching up to these topics. Yes.
Going to the Grassmannian, is it some sort of Tom isomorphism type thing, or?
So
Reducing the intersection theory on this bundle to some base, like some sort of.
So what happens? I will say it. It's exactly this point. What happens is you need Segre classes of symmetric squares of those bundles, and yeah, from one hand this is very hard, but from the other hand, fortunately, those 20 people thought about it. So they thought how to do intersection theory here. And I want you to teach it now on the next slide, how to do, at least what's the question? What's the down-to-earth question? How do you do intersection theory on such thing? So this symmetric power really means that if you have x1 to xn, you shouldn't think about this as variables. You should sum them up. This is what symmetric power does. So you have to evaluate a complete symmetric polynomial of degree d, but not on x1, x2, x3, but on sums. And the real question to compute those numbers is to get, so this is still a symmetric polynomial in xi's, and you want to write it in sure polynomial basis. There are some coefficients that you get. Maybe let me be even more explicit, yeah? I take a second symmetric polynomial, and I have two variables. So what are the sums? 2x1, x1 plus x2, and 2x2, okay? And now I take a complete symmetric polynomial, which means I have to square this, plus square this, plus square this, plus this times this, plus this times this, plus this times this. If I didn't do a mistake, it's such a symmetric polynomial. And now I have to write it in sure polynomials, which are complete symmetric polynomials and elementary symmetric polynomials. Okay, so there is a whole machinery how to get this 7 and how to get this 3. Intersection theories and Segre classes on Grassmannians, they reduce to such operations on symmetric polynomials. Yeah? So this is something very down to earth. And using such computations, you can answer those hard intersection theory problems. And in principle, I don't think that people tried. You could do the same for tensors to get their characteristic numbers. Certainly, people haven't tried for matroids because there you use a different theory. You use the theory of toric varieties, which simplifies calculations a lot. So I didn't do this in LaTeX, but I wanted to show you the whole triple diagram. So this is the part for matroids, where we have diagonal matrices inside P1 to the n. Yeah, so compared to the first slide, it's like rotated. This is the part for tensors. This is the part that I would like everyone from now on to work on. And this is the classical part by Schubert on complete quadrics, where our characteristic number, so in other words, characteristic number for a tensor coming from the space of symmetric matrices, they answer this classical enumerative problems. I hope I also persuaded you that for diagonal matrices and subspaces, they answer classical problems in combinatorics. I am not yet sure what they answer in the full tensor world. I should certainly say that all those invariants cohomology classes that we introduce, they are semi-continuous. So if you will find a cohomology class associated to one tensor and a cohomology class associated to a second tensor, if there will be a coefficient that is bigger for a second tensor, this proves you that you cannot degenerate one tensor to another. And this could be a new method to show that certain tensors don't degenerate to others. And tensor degeneration is essentially more generalization of tensor rank. Yeah? Tensor rank is a question of what kind of tensors a unit tensor degenerates. So did this work at all? Well, we have now several papers in statistics. Oh, I still have 8 minutes. I somehow thought I'm much worse with time. But then we have matroids. We have intersection theory. So I will spend last 8 minutes to do statistics. And I also want to tell you that those numbers are very important in statistics. So is this visible? This part? I mean, I will try to write in maybe red. So you probably know the Gaussian model and its distribution, right? So the distribution of the Gaussian model up to a scalar is given by E2 minus x squared divided by something. So there is a multi-dimensional generalization of it, where you take E2 minus x a xt, but, well, times a constant. And this is called a multivariate Gaussian model. But in order for this to be integrable, you know, it has to be a probability distribution. You want A to be positive definite. Okay. So this is just one distribution. Yeah, maybe you look at the sky and you see the stars, and maybe it follows some multivariate two-dimensional Gaussian distribution, how the stars are appearing. Yes, so I should say what's my task. The task is that I see the stars and I want to find the A that wins, that best describes it. But, you know, I know where is the mean. I can just take any place and I can add the vectors divided by the number of stars and shift it. So shifting the data by the vector, you can always assume that the mean is 0. Okay, so I will assume there is a hidden assumption that the mean is 0. And what's a statistical model? A statistical model tells you that maybe you want to pick your A from some prefixed set. Yeah? Maybe an astronomer knows that there will be no correlation between something. And a linear concentration model is when you take your A's from a linear space. So a linear concentration model is nothing else than a linear subspace of symmetric matrices. Okay? Now, what's our aim? Well, we have some data. Okay? And we have an L, and we want to find an A that best explains this data. but what does it mean, best explains? So we have our FA, and we can evaluate FA at every single point of the data, and maybe we would like to maximize this function. Okay, this is called the likelihood function, where if you have a data here, well, certainly you would like this peak to be around here. So the bigger the product of FAs on your data, the better. Product is hard, so you take the logarithm of the products. Okay, so this is called the log likelihood function, and you want to find an A which maximizes it. That's the aim in statistics, an A in L that maximizes such a log likelihood function. Well, how can you do it? You can compute partial derivatives, check the critical points, and check which one of them is the best one. But then what can an algebraist do with it? Well, I think this definition goes back to Sturmfels and Euler. You can ask how many critical points there are. So we heard talks about Euclidean distance degree. That is a different number of critical points, and this is called ML degree. And then there were papers that say that, oh, we conjecture that for this and that model, the ML degree should be given by such and such expression. So it turns out, remember, L is just a subspace of critical points. It turns out that often ML degree, or the degree of the model, which is yet another thing, they can be computed using our characteristic numbers. So you can use all this machinery that people developed in the last 50 years to prove those conjectures coming from algebraic statistics. Yeah, and this is what we did. So we computed certain degrees of statistical models. We can compute this thing by Schubert. So Schubert essentially told you how to do it, but how far you can actually do it, that's another thing. So with the development of this method, we can now really go much farther than before. We can compute ML degree. We can compute Euler characteristic of determinantal hypersurfaces. This is something I didn't talk you about. So if you have a matrix with linear forms and you want to know what's the locus of degenerate matrices, this is what people in computer science often want to know. For example, is your space of matrices contained in such a locus? Then the Euler characteristic is again expressible in our characteristic numbers. There is also something called algebraic degree of semi-definite programming, which tells you the degree of the extension in which solution to a semi-definite program could be found. Again, these are instances of our characteristic numbers. And very recently, students applied it to study finite algebras. So an algebra is also a tensor, because A times A multiplication map to A is a bilinear map. There is an associated tensor, and it turns out that from characteristic numbers you can read off such properties as being Gorenstein or locally complete intersection. And my first talk was that you can, of course, use it to study characteristic polynomials of matroids. And these are the works. So ML degree of a cyclic graphical Gaussian model. This was a conjecture by Sturmfels, Drton, Euler, maybe Sullivan, and proved recently by my PhD student and my postdoc. The degree of the cyclic graphical Gaussian model, that was a conjecture of Sturmfels and Euler. The ideal of the same model, that was with Kenjin Han, we proved it. So all these were really open conjectures, and this method really helped to solve them. If you would like a comprehensive study with Laurent, Leonid, Tim, and Jarek, there is a magic polynomiality jumping in. I started 5 minutes later, so maybe I will steal 3 minutes. You know Pascal triangle, right? It starts with like a 1 and the 1 and the 1 and the 1 and the 2 and the 1. right? Everyone knows Pascal triangle. So Pascal triangle has the property that if you look at it column-wise, it's a polynomial. Yeah, n choose k happens to be a polynomial. And so what's Pascal triangle? Well, Pascal triangle are characteristic numbers for the permutohedron if you just intersect with L1 and Ln minus 1. If you intersect the permutahedron with L1 and Ln minus 1. So you can ask what happens if you intersect complete quadrics with L1 and Ln minus 1. So what am I asking? I am asking in Pn, you take 7 general points and the correct number of general hyperplanes. There is only one number of hyperplanes I can take to get a number. And how many quadrics are tangent to hyperplane and pass through 7 general points. But now I change n. I change n. I keep the 7, but I change the n. And this was a conjecture that this is a polynomial in n. Sounds very strange, yeah? Because I'm doing a counting problem in another, and very funny, this conjecture was coming from algebraic statistics. It wasn't coming from algebraic geometry. The numbers that I'm talking about, you can find them 150 years ago in books by Schubert. He was computing some of them, but he would never put them in a triangle. He would read them row by row. So somehow fixing the dimension of the ambient space and checking. Only I take that many points. Then I take one hyperplane, and so on, and so on, and so on. But it turns out a very interesting pattern emerges when you do the quantum Pascal triangle, and the conjecture was that the columns are polynomial. So this is what we proved in this paper. And recently, I think for the first time, we managed to go back. So this theory in matroids is like really well developed, especially because Juni and his team are there. But this idea of translating between LIs and SIs is so clever that we managed to obtain some new results even in combinatorics using it. Thank you very much.
Okay, yeah, thank you. So comments or questions?
Relating to your favorite diagram, what is it when zigzags break at Grassmannians? What do you mean?
So you draw orbits, but it's not true that every orbit corresponds to a point in the Chow quotient. It is true that every point in the Chow quotient corresponds to a union of orbits. So it could be that the end of one orbit as t goes to infinity is the beginning of the other orbit as t goes to 0. And if you take such union of orbits and you start from V and go to V dual, this is exactly in bijection with all of the points, for example, here with CQ. So breaking, I mean that this orbit is really different from this orbit. It's not one orbit. These are 2 orbits. And it can break into many pieces. I should mention that many parts of this picture, they appeared in works of people. So, for example, such a picture with zigzag you can find in Tadeusz's work, very beautiful work.
Could you explain again what the algebraic degree of semi-definite programming is? And yeah.
Yes. So first, what's a spectrahedron? Well, it's a linear cut of a PSD cone. And then you might want to optimize a linear function over it, right? But, well, you know, if everything is defined over rationals for polytope, then the vertices of the polytope are also rational, and the linear function will be maximized at the rational point. For spectrahedra, this is not the case. The solution does not have to be rational, but it will live in some algebraic extension of Q. And you can ask in which one.
So what is the degree of the field extension? Oh, okay, thank you.
My final question, if there is one. Do you have
an example. So what would be the invariant if we consider tensors of, say, format 2 by 2 by 2?
Oh, so I should say we have now a computer program that computes the characteristic number. You can input your tensor. I think it works quite efficiently until 10 by 10 by 10. It's by Austin Conner, and you do get the characteristic numbers. For 2 by 2, I mean, I would have to do this. It's not that I know them by heart. I mean, but for cohomology classes in the Grassmannian, Matej had it, right? It depended, it really read off properties of the tensor. So it will depend, for example, on ranks of flattenings. Yeah, and small examples are certainly in our paper with Austin, so I can look it up in 60 seconds and I can give you the numbers.
May I ask? And so you talk about 3-order tensor, but if you look at 4th order and so on, so what do you do in this case?
I don't do anything in that case. I don't have any analogous picture for higher order tensors. So, okay, well, that's not completely true because, you know, just like quadrics are degree 2 polynomials, you could ask what happens for cubics that, for example, are tangent to points. And there's again, like a whole field. Okay, cubics seem like a 3-order tensor, but if you have a family of them, that's like a 4-order tensor. Ravi Vakil has papers there and so on. And there was another team of students that I was supervising that using similar techniques managed to obtain new results answering like questions of type how many cubics pass through a given number of points are tangent to a given number of lines and so on and so on. And the part of the work was to try to define the space of complete cubics. But this is super hard. So they managed to do it in some small cases. It's essentially the level of difficulty of going from 3 tensors to 4 tensors is like going from matrices to tensors, 3 tensors, which we know is like a very different story.
Great, yeah. So thanks again.
Thank you.